Welcome to this new activity, which is about constraint optimization using Lagrange multipliers. So we have a rectangular box with no top and two intersecting partitions to be constructed from 192 square inches of cardboard. The question is find the dimensions that will maximize the volume. Before starting this problem, we have to set our variables, which are the dimensions of the box. So let's set x, y, and z as variables. So the x is the width, the y is the length, let's say, and the z is the height of this box. Now, the volume of the box is x times y times z. So the problem is to maximize the function v, which is the volume, which is equal to x times y times z. But here we will not maximize it without a constraint. We have to maximize it with this constraint, which is the surface or the area of the cardboard available, which is 192. First, we have to find the surface used using the x, y, and z variables. We have the bottom surface, which is equal to x times y. So if we want to write the surface of this box, we're gonna write it as x times y, which represents the bottom of the box, plus, and here we can see that we have three sides which are equal here. Okay, these three sides have an area of x times z, and they are repeated three times, so we have plus 3x times z plus, and if you look to your box again, you have these three sides which are equal also, and each one of them is z times y. So we have plus 3 times y z. This is the surface. It must be equal to 192. So our maximization problem is maximize v subject to the condition xy plus 3xz plus 3yz equals 192. Now we're going to use Lagrange multipliers to solve this. Okay. First of all, you have to write your constraint as a function g of xy equals 0. So let's write our constraint g of xy equals xy plus 3xz plus 3yz minus 192 equals 0. So this is the first step. The second step is to construct our capital F function. So here we have x, y, and z variables, and we have to include a fourth variable here, lambda, and we construct fxyz lambda as the volume, which is xyz, the objective function, plus lambda times the constraint g of x and y and z. Sorry, I forgot the z here. Okay, sorry. So plus lambda times xy plus 3xz plus 3yz minus 192. The next step is to compute the partial derivatives of the capital F function with respect to x, y, z, and lambda. So let's write our system. So fx is equal to yz plus lambda y plus 3 lambda z. So it's equal to yz plus, we'll put the lambda as a factor, lambda factor of y plus 3z. The second partial derivative is fy. It can be written as xz plus lambda x plus 3 lambda z. So it can be written as xz plus lambda factor of x plus 3z. The third one is fz, and here it's equal to xy plus 3 lambda x plus 3 lambda y. And here again, we can put the lambda as a factor, so it's xy plus lambda factor of 3x plus 3y. The last one is f lambda, and f lambda is xy plus 3xz plus 3yz minus 192. Okay, now we have to set our partial derivatives equal to 0. And I will number my equations here. Equation number 1, 2, 3, and fourth equation. Okay, I can see clearly that the y and the x will play the same role, since the first and the second equation are symmetric with respect to x and y. Okay, so by looking, the x and the y play the same role, so we're gonna prove that x equals y. But first, let's write from equation 1 that lambda is equal to negative yz over y plus 3z. From equation number 2, we can conclude that lambda equals negative xz over x plus 3z. Now, if you take the equality between these two quantities, since they are equal to lambda, and remove the minus sign because it appears in both, we can write that yz over y plus 3z equals xz over x plus 3z. Here we're gonna develop, so y z times x plus 3z will be equal to xz times y plus 3z. Of course, we can expand again. We'll obtain x, y, z plus 3y z squared equals x, y, z plus 3x z squared. Here we can cancel the x, y, z from both sides. We can cancel the z squared because the z is not equal to 0, so we can cancel it here. The z represents the height, so it's different from 0, okay? And we can cancel the 3, and the conclusion is that y equals x, okay? Now, we concluded that x equals y, and we're gonna use this equality in the next steps. Now, I will use the second and the third equality here, okay? But first, let's number, okay? So from the second and the third equations, we have, so let's take the second and the third equation to the next page, and keep in mind that we have x equals y, okay? Now, I will use the equality x equals y. So I can write the second equation here from equation number 2. I can write that xz plus lambda times x plus 3z. It gives that lambda equals minus xz over x plus 3z. And from the third equation, we conclude that we have xy, and since x equals y, we can write it as x squared plus lambda times 3x plus, and here again you replace the y by x, you will get plus 3x again, which is 6x, okay, equals 0, of course, here and here. So you conclude here that the lambda is equal to x squared, or negative x squared, sorry, over 6x, okay, which means that lambda equals negative x over 6, okay. Now you have lambda here and here, you can write the equality between the two quantities, okay. So let's write that negative x over 6, which is the second expression of lambda, equals the first one, and we can remove the minus signs because it appears in both, okay. We can write that x over 6 equals x times z over x plus 3z. Here, of course, we can cancel the x, since it's not equal to 0, and we'll get that 6z equals x plus 3z, and from this, if you cancel 3z from both sides, you can conclude that 3z equals x. So this is the second important relationship between variables, okay. We have x equals y, and now we have x equals 3z. Now I will include this equality in the fourth equation. So back to the equations, to our system, and take the fourth equation, this one, okay. And here, keep in mind that you have x equals y and x equals 3z. We concluded this from the previous work, okay. So x times y is x squared plus 3 times x times z, and z is equal, so if x is equal to 3z, z is equal to x over 3. So you will get 3 times x over 3 plus 3, and of course you can replace the y by x and the z by x over 3, equals 192, okay. Now you will obtain x squared plus the 3 will be cancelled, and you will obtain x squared again here, and plus again x squared if you cancel the 3, plus x squared equals 192, which means that 3x squared equals 192, which means that x squared equals 64. 192 over 3, which is 64, and therefore x is equal to 8. You exclude the minus 8 value because the x is a dimension, it's positive. So you found that x equals 8 inches, okay? Remember that the y is equal to x, so y is also 8 inches, and z is equal to x over 3, so it's equal to 8 over 3 inches. So we obtain the dimensions which will maximize the volume in this case, okay? Thank you for your attention, guys, and see you in the next videos.